Yeah, I can see it now. Thank you. And Jeff, are you planning to play the video or?
I'm trying. I'm trying right now. Yep.
Yeah, I can see your screen.
Right.
Remember to share your
Hello
picture.
everyone, this is Yuxiong. Welcome to DeepSpeed tutorial.
Is the audio
DeepSpeed
playing as
is
well?
a deep learning training optimization library. It
Yes.
makes DL training easy, efficient, and effective. It allows you to train PyTorch models with 100 billion parameters up to 10x faster with minimum code changes. Today, my colleagues Samyam, Jeff, Tanji, and I will share with you our exciting features of DeepSpeed and how to use it to accelerate and scale up your model. I will start the tutorial with an overview of DeepSpeed. In the overview, I will start from why we developed DeepSpeed and what it is. Then I will go over some highlights of results and the underlying techniques that deliver those results. After that, I'll talk about how we put these techniques together in our software architecture. That concludes the overview of DeepSpeed, and then I'll give a preview for the rest of the tutorial sessions. A key challenge in DL training is that it's too slow to train high-quality model with massive data. More specifically, more hardware may not bring higher throughput. For example, when computation is a bottleneck, when model size exceeds device size. Furthermore, higher system throughput doesn't indicate faster convergence. That's where the dark part of deep learning kicks in, where techniques such as large batch scaling, gradient compression improves performance but could slow down convergence. The last but not the least, the optimization ideas and techniques are often scattered. How to use them collectively and conveniently is non-trivial. This motivates our work on DeepSpeed. Directly target on the challenges we observe, striking for 3 E's on training: efficiency, effectiveness, and easy to use. Efficiency promotes efficient use of hardware resources to obtain high throughput on single GPU and linear scalability across GPUs. This covers the HPC part of the DL system. Effectiveness strives for high accuracy and fast convergence. We want to reduce training samples, therefore the cost to achieve high accuracy. This is where machine learning theory meets system performance. Easy to use make efficiency and effectiveness conveniently accessible to data scientists, improving development productivity. So what is DeepSpeed? DeepSpeed is a DL training optimization library. On the software stack, DeepSpeed is an optimization layer standing between DL model and training framework. Among the frameworks, we primarily support PyTorch. Users can leverage performance benefit of DeepSpeed with just a few lines of code changes on their PyTorch model. Here is an example of BERT model. We show the changes required to use DeepSpeed. The primary change is to call DeepSpeed initialize to wrap the model and optimizer. Then we can think of this wrapped model as DeepSpeed and Jing. With similar syntax as original, it's used for forward pass, backward pass, and parameter update. And that's it, minimum code changes. Then DeepSpeed will handle the underlying performance challenges and apply its efficiency and effectiveness optimizations. That leads to speed and scale. What kind of speed and scale? Let's take a look of the result highlight of DeepSpeed. DeepSpeed excels in 4 areas: model scale, training speed, scalability, and usability. With respect to model scale, state-of-the-art large models such as NVIDIA Megatron-LM and Google T5 have size of 8 billion and 11 billion parameters. DeepSpeed introduced a system breakthrough 0, standing for Zero Redundancy Optimizer, to conquer the memory and scaling challenge of very large models. 0 significantly reduced memory footprint while retaining compute and communication efficiency. In the first stage, 0.1 imparts DeepSpeed to run 100 billion parameter models efficiently, 10x bigger than the largest published model by then. Leveraging this unique system capability, DeepSpeed powered model training of Turing NLG 17 billion parameter model, the largest model until May this year, and obtained record-breaking accuracy. We continue to push for the frontier of training system. In early May, we released the 02, which adds novel memory optimization on top of 01 and unblocks 200 billion parameter model training on today's hardware. Very recently, we heard GPT-3 from OpenAI. It has a record-breaking model size of 175 billion parameters. I want to point out that the system capability of 02 would allow us to run such gigantic models. Furthermore, we are looking closely on 03, which could allow us to scale to models of arbitrary size as long as aggregated memory of hardware allows. For example, running 1 trillion parameter using 1,000 GPUs. Please stay tuned for that. Besides scale, DeepSpeed also excels in speed. For very large models, such as those over 25 billion parameters, we observe up to 10x faster throughput over Megatron-LM, a state-of-the-art model parallelism approach. For example, the figure here shows a system throughput using DeepSpeed versus Megatron-LM. The workload is a GPT family of model with size from 40 to 170 billion parameters. Here, the throughput of Megatron-LM is normalized as 1x shown as green bar. The throughput of DeepSpeed are shown as blue bars. Megatron-LM used tensor slicing for model parallelism, primarily optimized for intranode parallelism. For models over 25 billion parameters, Megatron needs to run them across nodes. Smaller internode network bandwidth significantly degraded its performance. On the other hand, DeepSpeed combines zero-power data parallelism together with tensor slicing of Megatron. Zero improves memory efficiency. It fits the models using lower degree of model parallelism and allows for larger batch sizes, improving both computation and communication. That leads to up to 10x higher throughput. With respect to scalability, we have an interesting observation. For people working on systems, it's normal to see sublinear speedup with an increasing number of devices. Perfect linear scalability is probably the best to expect. Can we do even better? The answer is yes, sometimes with DeepSpeed. The figure shows our system scalability with an increasing number of GPUs. The green curve shows the scalability assuming perfect linear speedup. The blue curve shows the measured scalability results with DeepSpeed. We can see that our measured scalability is above the perfect linear speedup line, achieving superlinear speedup. In other words, when we double the machines, we more than double the system throughput. So what's going on? This comes from the power of zero. When we increase number of GPUs, we reduce the memory required per GPU to store model states. So there are more device memory available for activations. That allows higher batch size and potentially higher GPU efficiency, and it brings superlinear speedup. When we scale models towards many devices, such superlinear speedup could reduce the training time substantially. Last but definitely not the least, DeepSpeed is easy to use. With only a few lines of code changes, we can enable a PyTorch model to use DeepSpeed, as we showed as a previous BERT example. Furthermore, to train large models, how to use model parallelism impose major constraints. DeepSpeed alleviates this burden from our users. For models up to 13 billion parameters, users can just use or love data parallelism without requiring model parallelism. In contrast, without DeepSpeed, models beyond 1.4 billion will run out of memory with data parallelism alone. In summary, we develop and share DeepSpeed to offer exceptional scale, speed, scalability, and good usability. Now, taking one step further, this slide shows some key optimization techniques that power the performance of DeepSpeed. I list them in three categories: features for efficiency, effectiveness, and easy to use. First, Efficiency features are those that improve throughput and scalability of the system. For example, zero redundancy optimizer for memory efficiency, ultra-fast transformer kernels for compute efficiency, sparse gradient for communication efficiency, overlapping I/O with compute for I/O efficiency, flexible combination of data and model parallelism for scaling efficiency. Second, effectiveness features are those that improve convergence. For example, adaptive hyperparameter tuning with appropriate warm-up and decay optimizers for large batch training. Third, usability features that make the efficiency and effectiveness accessible to our model scientists. For example, DeepSpeed sets up all the boilerplate training techniques, such as distributed training, mixed precision, gradient accumulation, and checkpointing, such that our model scientists can focus on the model development. It also simplifies the data loader to support auto batch creation for models combining different types of parallelisms. It supports checkpoint and recompute to facilitate long training and large job training. It provides convenient APIs to perform performance breakdown and profiling, all of which are critical for training large jobs. Later in the tutorial, we will show a few techniques in more details. This slide shows the software architecture of DeepSpeed. We'll talk about how we put the optimization techniques together in the software stack. DeepSpeed consists of three parts: APIs, runtime, and operators. DeepSpeed API is a thin wrapper compatible with PyTorch, so PyTorch users can enable DeepSpeed with just a few lines of code changes. As we have briefly seen, the main function is DeepSpeed.initialize. It also has a parameter JSON file that's used to define training configurations. We will show concrete examples of them in the later session when we talk about how to use DeepSpeed. The second component of DeepSpeed is DeepSpeed Runtime. This is a core part to manage job execution and perform optimization. It deploys training jobs across distributed devices, performing data and model partitioning. It consists most of system optimization, such as memory, communication, interleaving of I/O, and compute. It also has tuning modules for effectiveness and utility module for failure detection, checkpointing, and so on. DeepSpeed Runtime is written in Python. DeepSpeed Ops is the C++ and the CUDA layer with low-level kernels for computation and communication. For example, ultra-fast transformer kernels, fused LAM kernels, customed or reduced. So these are the key components of DeepSpeed. Next, I want to point out the rationale behind this software architecture and its benefit. First, we layer our optimization on top of the training framework versus closely coupled. This allows us to leverage existing ecosystem for fast innovation, while it's so much easier to maintain than deep integration into PyTorch. Furthermore, DeepSpeed is agnostic to training infrastructure, so our users can leverage it across many different training infrastructure as they desire, such as Azure ML, Azure VMs, MPI-based platforms, and other local machines. So far, we have completed the overview of DeepSpeed. Next, let me give a preview on the rest of the tutorial sessions. Over there, we'll zoom into the key results and optimization techniques through 3 examples. First example shows how DeepSpeed supports and accelerates large model training, Turing NLG 17 billion parameter model. Here we will deep dive into our novel memory optimization technique, Zero, standing for Zero Redundancy Optimizer. It reduces memory footprint of large models, improving both communication and computation efficiency. In the example of Turing NLG, we obtained 3x higher throughput compared with digital arts. We'll also talk about how DeepSpeed supports flexible combination of different types of parallelism, allowing us to scale to bigger models and more devices. We complete this example with some interesting demo of leveraging Turing NLG for free-form generation, QA, and summarization tasks. Second example shows how DeepSpeed achieves the world's fastest BERT training record, 44 minutes on 1024 GPUs. We are more than 30% faster and more efficient comparing with the already very competitive state of the art. We'll go over our key optimization techniques to improve efficiency, such as ultra-fast transformer kernels and sparse output computation, as well as a few convergence optimization techniques to reduce the total training samples required to get desired accuracy. The third example is one of our production models. We will show a few key techniques such as sparse gradient and advanced hyperparameter tuning, which leads to an order of magnitude training speed up. Hopefully, these examples give you a concrete view on the capability of DeepSpeed on improving training speed and scale. With that, we will move to a step-by-step instruction on how to use DeepSpeed from installation to applying our APIs to U models to run and evaluate them. Finally, we'll address a few frequently asked questions about DeepSpeed. Thank you for having DeepSpeed tutorial with us. Next, I will turn the floor to Samyam to talk about large model training using DeepSpeed.
Welcome back, everyone. So now in this final chapter, we'll be going through how to use
Right. Thanks, everybody.
the trained models to do inference.
Next segment here.
Hello, everyone. Welcome back to the DeepSpeed tutorial. My name is Samyam Rajbhandari. And hello, everyone. Welcome back to the DeepSpeed tutorial. In this section, I will be giving a short demo on the Turing NLG 17 billion language model. My name is Hello, everyone. Welcome back to the DeepSpeed tutorial. My name is Samyam Rajbhandari, and I am a researcher and an engineer at the DeepSpeed team at Microsoft. And today I'll be talking about how DeepSpeed enables large model training, and I'll be using the Turing NLG 17 billion model as the guiding example. So in this portion of the talk, we're primarily going to talk about the key techniques inside DeepSpeed that allows us to train really massive models. We'll talk about how DeepSpeed can work with model parallelism techniques that are already out there. And at the end, I'll give a short demo of this Turing NLG 17 billion model. It's quite impressive what the model can do, so stay tuned for that. All right. So a few months back, we trained the Turing NLG 17.2 billion model at Microsoft. This is a GPT-2 style language model constructed using multiple layers of the transformer blocks. So this model is quite massive, and given the amount of resources required to train this model, initially it was quite impossible to do so. But with DeepSpeed and the large model training optimizations inside DeepSpeed, we were able to significantly reduce the amount of resources required to train this model. And with that reduced resources, we were actually achieving 3 times the efficiency of the state-of-the-art systems at that time, which allowed us to train this model. So before we get into the details, just to give you all a sense of how big this model is, the table in this slide compares the Turing NLG model with the BERT large and the GPT-2. So you can see that each iteration each sample of the Turing NLG model has about 100 times more compute than the BERT large. And the memory footprint of the model, including the parameters, the gradients, and the optimizer states, that alone takes about 275 gigabytes of memory. This is clearly much larger than the amount of memory that is available on a single GPU. So you need to train this model using some kind of a model parallelism that splits the parameters and the gradients and the optimizers across multiple GPUs. So one approach, and the most promising approach that we could find at the time for training this model, parallelism splits the model across multiple GPUs. It splits the computation across multiple GPUs. And by doing that, it's able to reduce the memory footprint required per GPU. And so here in this table, we're showing the state-of-the-art model parallelism framework. You can really by that framework to train this model. This framework is called Megatron. So with Megatron, you could train this model on a DGX2 cluster where each one of the nodes in the cluster has 16 V100 GPUs, each with 32 gigabytes of memory. You could train it with Megatron, but you would need a 16-way model parallelism to train this model, to just fit the model in the GPUs. And even after splitting this model into 16 different pieces, you could only train with a batch size of 8 per node, which meant that in order to train this model with a reasonable batch size, so in general, these language models are trained with a batch size of 512 or larger. So just to train with a batch size of 512, you would need a total of 1,024 GPUs, and that's a lot of GPUs. And even with that, we were only seeing about 9 teraflops of performance per GPU. So 9 teraflops is less than 10% of the peak performance of these V100 GPUs, which means that not only we needed massive amounts of GPU, our efficiency was also very low. So that made it infeasible to train this model with the state of the art. So to address this, we developed a memory optimization technology that is called the Zero Redundancy Optimizer, which is now in DeepSpeed. And with this technology, combined with the model parallelism of Megatron, we were able to train this model. So on the right column, we're showing the configurations. With Zero, we're able to reduce the model parallelism to 4 from 16. And even after reducing the model parallelism degree, we could still fit a batch size of 32 per node, which meant that now you can train this model with an aggregate batch size of 512 with just 256 GPUs. And each GPU is now achieving over 30 teraflops in performance. And so now it's possible to train this model because we are not only reducing the number of resources, but we are also getting quite high efficiency. So one thing I want to point out is that when you decrease the model parallelism degree, the granularity of the computation increases per GPU. And also because we are increasing the batch size, that also increases the granularity of the computation, as well as it improves the compute to communication ratio, which is very important for performance. And so we are able to achieve this high efficiency of 30 teraflops per GPU because of the improvement or the increase in computational granularity from decrease in model parallelism and increase in compute to communication ratio from an increase in batch size. Okay, so then the next natural question is, how is Zero able to reduce the memory footprint of the training? So before we get into that, let's take a quick overview of the distributed data parallel training. This is the backbone for training large models or even moderate-sized models across multiple GPUs. So in general, we're trying to run this data parallel loop shown on the left on a distributed GPU cluster of some sort shown on the right. So in the distributed GPU cluster, each node can have multiple GPUs connected with internode interconnect, and each one of these nodes are connected to each other with the internode interconnect, such as InfiniBand. And so what we're trying to do is trying to run this loop on the left on each one of these GPUs. On each GPU, we are loading a different mini batch from our data. We compute the forward propagation on that mini batch. We compute the loss. We compute the backward propagation, which computes the gradients. So now each GPU has its own set of gradients computed from its mini batch. So now we average these gradients across all these GPUs. Now at this point, each GPU has the same gradients. So now it uses that gradients to perform the optimizer specific updates, and it will apply those updates to the model. And so one thing to notice is that we start off by replicating the model and the optimizer states across all these GPUs. And so since we're starting off with the same model parameters and the optimizer states, and we're updating them with the same gradients, at the end of each step, the parameters on all GPUs are always consistent. So if we look at this carefully, one thing we notice is that each GPU contains the same replica of the model and optimizer states. So in other words, the model, the optimizer states, and the average gradients are all redundant across the GPUs. So here we have a figure that shows the memory map of 0 along with the baseline data parallelism that we just talked about. The very first row shows the baseline memory map for data parallel training across multiple GPUs. Each GPU has a replicated copy of the parameters, the gradients, as well as the optimizer states. So the way the zero redundancy optimizer is able to reduce the memory footprint is by removing this redundancy, and it does so by partitioning the parameters and the gradients and the optimizer states across these GPUs instead of replicating them. So during the training, we have these 3 different model states that we've been talking about, the optimizer, gradient, and the parameters. And so corresponding to each one of them, the zero redundancy optimizer also has 3 different stages. The first stage partitions only the optimizer states. The second stage partitions both the optimizer states and the gradients. And the third stage partitions all 3 of them. So here we're first initially just going to look at the very first stage of the zero redundancy optimizer that only partitions the optimizer states. Okay. So stage 1, zero redundancy optimizer. So in stage 1, all the computation happens just normally like in the standard data parallelism. Each GPU will load a different mini batch. It's going to do the forward propagation and backward propagation, and it's going to communicate those gradients. And so once these gradients are averaged, each one of the GPUs has these replicated copies of the gradients. Now, unlike in data parallelism, where each GPU was updating all the parameters, in zero stage 1, each GPU only updates the portion of the parameters that it owns. So remember, the optimizer states are already partitioned. So because the optimizer states are already partitioned, there is a small portion of the total parameter set that it can actually update. So it will only update that part. Once it has updated that part, we can do an all gather of the parameters so that each GPU now has all the parameters that are now updated. Okay, so let's take a look at this in a bit more detail. So here, let's assume we have 2 GPUs and we're trying to train a 16-layer Turing NLR or a BERT-like model on these 2 GPUs. And these are transformer-based models. So each of these gray cells represents each one of the transformer layers. So now these smaller square cells represents the memory consumed by different components during training. The blue cells represents FP16 parameters. So let's also assume that we're doing mixed precision training here, which means the parameters themselves stay in 16-bit during the computation, but then the optimizer states and the weight updates actually happen in FP32. So we have these blue cells representing the FP16 parameters. Then we have these orange cells representing the FP16 gradients. Then we have all these green cells representing FP32 gradients. If we're using an optimizer like the Atom optimizer, which is very common for training NLG models, then we're using the FP32 variance and momentum, which are the part of the optimizer states, and we also have the FP32 parameters. So this is standard data parallelism. Now with also we have the activations. So these blue cells represents the activations during the training. So this is standard data parallelism. For 0 stage 1, we're partitioning the optimizer states, which means each GPU only stores half of the total optimizer states. So now, during the training itself, we proceed as normal. We compute the forward propagation. We compute the loss. Then based on the loss, we compute the backward propagation, and that computes the gradients. Now, once the gradients are computed, GPU 1 can send the first half of the gradients to GPU 0, and GPU 0 can send the second half of the gradients to GPU 1. Each GPU only needs half of the gradients because that's only the amount of weights that it's going to update. So now those gradients can be averaged. Then once you have the average gradients, now each GPU can proceed in parallel to update its optimizer states and its FP32 parameters. So now that you've updated your FP32 parameters, you can copy that back to your FP16 parameters, and finally you can do an all gather. So GPU 0 will send the first half of the parameters to GPU 1, and GPU 1 will send the second half of the parameters to GPU 0, and that completes one iteration with 0 stage 1. So with 0 stage 1, depending on the kind of optimizer you're using and whether you're using mixed precision or not, you can get up to 4x memory reduction. In general, for mixed precision training, and if you're using the Atom optimizer, the optimizer states themselves cost 3 times as much as the parameter and the gradients, so there is a total memory reduction of 4 times. So earlier we said we trained this Turing NLG model using 0 and a model parallelism. So we trained this model with 0 stage 1 and the model parallelism in Megatron. So in order to do that, DeepSpeed can support tensor slicing based model parallelism techniques such as the Megatron LM. And it can do so by supporting this object called MPU, Model Parallel Unit. What this object does is it implements these 2 methods, get data parallel group and get model parallel group. The first method just tells DeepSpeed which processes are involved in data parallel training, and the second method, the get model parallel group, tells DeepSpeed which methods are involved in model parallel training. So using this information, DeepSpeed can coordinate with any tensor slicing based model parallelism implementation. It can use the 0 optimizer, and it can combine these 2 together to train the model. DeepSpeed doesn't need to know how model parallelism is implemented. It just needs to know which processes are involved in model parallelism training. So with that, here's just a table from the beginning. We were able to train this Turing NLG 17 billion model using 0 and model parallelism from Megatron. The 0 allowed us to reduce the memory footprint by a factor of 4, allowing us to reduce the model parallelism required to train this model while also increasing the batch size that could be trained. And this reduction in model parallelism and increase in batch size allowed us to attain a much higher efficiency than possible before, and while also reducing the number of GPUs required to train this model from 1024 to 256. And so we were able to train this model in a reasonable time with reasonable amount of resources. All right. So earlier we said the zero redundancy optimizer has 3 different stages. So far we talked about the very first stage of zero. So these 3 different stages offer progressive memory savings. The first stage, as we talked about earlier, reduces the memory footprint by a factor of 4. The second stage reduces the memory by a factor of 8. And then the final stage actually reduces the memory footprint linear to the number of GPUs that you have. So, so if you have 100 GPUs, that's 100x reduction in memory footprint. If you have 1,000 GPUs, that's 1,000x reduction in memory footprint. So a natural question to ask is, if we are reducing the memory footprint, are we trading that off by increasing the communication volume required for the training? So the table here shows the communication volume of these different stages of zero in comparison to the baseline data parallel. And we can see that the first 2 stages of zero incurs no additional communication volume compared to the data parallel training. Which means there is no penalty. We're getting this memory reduction for absolutely free. However, when we do go to zero stage 3, there is a modest increase in communication volume. There is about a 50% increase in communication volume compared to the data parallel training. However, in most cases, we should be able to overlap that communication with the compute and hide that communication volume. So currently in DeepSpeed, we've implemented the zero stage 2 optimizer. So far, we talked about how the zero optimizer reduces the memory footprint by partitioning the optimizer states, gradients, and the parameters. But in addition to that, the 0-2 in DeepSpeed also has a bunch of other memory optimizations. For example, it can reduce the activation memory footprint when you're training the model using model parallelism by partitioning the activations that are replicated across model parallelism processes. In general, when you train a model with model parallelism, the parameters themselves are already partitioned, but in a lot of cases, the activations could be replicated, and zero can partition those activations and reduce the memory footprint proportional to the amount of processes involved in model parallelism. It can also offload these activations to the CPU memory so that you can reduce the activation memory footprint further. The third optimization that zero can do is memory defragmentation. So during the training, as you're performing your forward propagation and backward propagation, certain memory are short-lived and certain memory are long-lived. And that is especially true if you are using something like activation checkpointing or gradient checkpointing, where you are only storing a few activations, but not all the activations. So during the training, as you proceed, you are creating all these working memory that gets released pretty quickly, but you're storing activations that are required for the backward propagation. So this interleaving of short-term memory and long-term memory can cause the GPU memory to fragment. And if you have a lot of memory fragmentation, then you can run into out-of-memory issues, even though your GPU has enough memory to train the model. So imagine your memory is fragmented so that now the biggest contiguous piece of memory that you have is 500 megabytes, even though you may have 4 gigabytes of total memory available on the GPU. So now if you're trying to allocate 2 gigabytes of memory, even though you do have 4 gigabytes of free memory, there is no contiguous 2 gigabytes of memory available on the GPU, so you can run into memory fragmentation issues. So 0 can, on the fly, defragment the memory during training, allowing it to fully utilize the GPU memory. So with the 0 stage 2 and all these different optimizations in 0, DeepSpeed can train models up to 200 billion parameters, 10 times faster than the current state of the art. And while this is pretty cool, we are still just scratching the surface of what 0 can do. Remember, we were talking earlier about 0 stage 3. And with 0 stage 3, we can reduce the memory footprint by another factor of 10, allowing us to even increase the model sizes that we can train. So while we don't have 0 stage 3 in DeepSpeed right now, that's what we are working on, and we ask you guys to stay tuned for when we will have that in DeepSpeed. But here I wanted to just show a quick animation of how 0 stage 3 works. Earlier we looked at how 0 stage 1 works. Now stage 3 combines both stage 1, stage 2, as well as the parameter partitioning. So here is a short animation. Once again, we're training a transformer-based model with 16 transformers. Here we're training this model on 4 different GPUs. And as you can see, each GPU only holds 1/4 of the parameters, gradients, and the activation. So let's take a look at how this works. So initially, before you can start the forward propagation, the GPU that holds the parameter for a particular layer needs to broadcast those parameters to all the other GPUs before the forward for those layers can happen. So here GPU 3 is broadcasting its parameters to all the other GPUs so that the last 4 layers of the transformer can execute. So now after the forward pass, the same thing needs to happen in the reverse order to compute the backward pass. During the backward pass, once the gradients for a particular layer has been computed, those gradients are then reduced at the GPU that will eventually update those parameters. So for example, here, everyone is sending the gradients to GPU 1. And then finally, we're computing the gradients for the first 4 layers, and each GPU sends those gradients to the first GPU. Now that each partition has the average gradients, it can update its corresponding weights, and with that, all the parameters are updated, and you can start the next iteration. So that's it for this part of the presentation. And next, we're gonna take a quick break and take a look at the Turing NLG demo. So stay tuned. Samyam Rajbhandari. I am a researcher and an engineer at the DeepSpeed team at Microsoft. Okay, so as we talked in the previous part of the tutorial, Turing NLG 17 billion model is a language model built by stacking multiple layers of transformers, very similar to a GPT-2 type model, and it's a language model, so it's great at doing generational tasks. So here we have the Turing NLG demo page, and we can do 3 different tasks with the Turing NLG model. We can do text summarization. So you give it a passage and it will summarize that for you. You can do answer synthesis, where you give it a question and a context passage, which contains the answer to the question, and it can extract that answer for you. And the part that I find most intriguing and exciting is the freeform generation, where you give it a prompt and it will continue to generate text based on what you give it. I do want to point out that what it generates is not always going to be factual, and in fact, for a lot of freeform generation, we're not giving it any context. We're just asking it to generate text based on what it has learned during the training. So it has seen so much data that it knows a lot of information about the world, about grammar, about basically just a lot of stuff that books that it has gone through. We trained this model on Wikipedia and the book corpus, so it has in some sense memorized a large portion of it. So when it's trying to generate, it's trying to generate from what it has seen during the training for the freeform generation part. So let's start with the summarization task. Here, let's just try something that that's already here. Romeo and Juliet plot summary. So here we have the passage storyline for Romeo and Juliet, and it tries to generate the summary for it. Romeo sneaks into a party, falls in love with Juliet. Juliet's parents arrange for her to marry Paris. Romeo poisons himself. Juliet wakes up and stabs herself. And that's a pretty decent summary of the passage here. Let's try answer synthesis. We're just gonna go over these quickly, and then we're gonna spend most of our time on the freeform generation. So let's try here. Let's try space news. Okay, so the question is, where did the astronaut grow up? And there is a passage, and the result says Christina Koch grew up in Jacksonville, North Carolina. So I've seen this before. So one thing that I find interesting is that the question is asking for where the astronaut grew up. It's not asking for where Christina grew up, and there is nowhere in the passage where it says the astronaut grew up in Jacksonville, but it does say NASA astronaut Christina Koch, and then later on in the passage we have this sentence here: Koch grew up in Jacksonville, North Carolina. And so it's able to figure out that the astronaut we're talking about is Christina Koch, and it's able to connect that with this. And it also knows that the NC here means North Carolina. All right, so that was answer synthesis. Let's take a look at the freeform generation part. Okay, so for this part, I have a bunch of prompts that I would like to try out. All right, so let's try this one. Who is the most loved cartoon character? And let's see what it says. Okay. That's interesting that it's making a distinction between who's the most loved character versus the most famous character. Okay, so let's try something else. I have this prompt: I love a good thunderstorm, don't you? Let's see what it says. And sometimes it may not make sense, or sometimes it may not be factual, but most of the time it's pretty coherent on what it generates. Right. And I guess the most impressive thing for me is that there is no context. It's just the model that's generating. It's the model that that's just completely generating stuff from the things that it has seen during the training. All right, cool. Yeah, so it understands what a thunderstorm is. It understands that there are lightnings during a thunderstorm and so on. Okay, so let's try something that's a little bit more romantic. Let's see what it says. Yeah, if I read the first few sentences, I wouldn't know that a language generated this, a language model generated this. All right, cool. So let's try asking it something that requires more factual knowledge. And so a lot of these prompts, I've tried them before. In a bit, we'll try something that I haven't seen before. So, but even though I've seen it, every time you ask it to generate, it will generate something new. Sometimes it will generate the same thing, but sometimes it will generate something new. But I guess like if we just try this same prompt again. Yeah, so it will just start generating something completely different here. But let's ask for a factual question and see what it says. Yep, so Edmund Hillary and Tenzing Norgay were the first people to climb, and it did get one of them right. And I've seen this before, that if we try it multiple times, it may not get it right. But it right now thinks it's a question and answer format, so it's now starting to generate its own question and answering them. So let's try something different. Let's see if it can generate a poem. So here is a poem by Edmund Waller, and let's see what it does if you give the model this. Yeah, so it tries. It understands it's a poem, and yeah. All right, cool. For the next next task, here I have a bunch of question and answers, and then at the end there is no answer. So we'll see what it does if we give it this. All right, so it's kind of understood that A is for answer, and then now it just continues to create its own questions and starts answering them. Yep, and here you can see it's not generating factual answers. All right, cool. So if, in case you guys are wondering if I have seen this before, yes, I've tried this before, and like I said earlier, it does give a different answer every time. But I wanted to also kind of try something that I haven't seen before. So here I have a page of random quotations. Every time I refresh this page, it generates a bunch of new quotations. So I'll just pick a few from here and then see what it does. So let's see. Okay, real success is finding your life work in the work that you love. Let's try this one. Yeah, so it's trying to make sense of it, but yeah. Right. So I feel like it has seen a lot of these question and answering scenarios. So sometimes it gets into this question and answering mode and just starts asking questions and answering itself. Let's try something else. The universe is a big place, perhaps the biggest. Let's try this. All right, I think this is pretty cool. Universe is a big place, perhaps the biggest, but it's kind of telling us that, well, maybe the existence of multiverses, if you think about multiverses, they're bigger. So that's kind of interesting that it's read a lot of physics text and it can connect the multiverse with the universe and the size as well. All right, let's try one more. Let's see, something short. Okay, self-confidence is the first prerequisite to great undertakings. Let's try that. Right, that's cool. Okay, so let's go back, and I want to end this demo with a few lines from the song Imagine. Once again, there is no context here, but if you give it the song, it actually recognizes the song because it must have seen it during the training, probably numerous times, and it just continues on with the lyrics. And I thought it would be a nice place to end this demo because this model and this generation capability really makes me think and imagine the kind of things that we can do with powerful models like this, and where we can go by the advancement of these large generative models. All right, thank you guys for tuning in, and hopefully you enjoyed the demo and have a good rest of the tutorial with the DeepSpeed. Thank you. Hello everyone. Welcome back to the DeepSpeed tutorial.
Now, I'll discuss how we achieve the fastest BERT training time using DeepSpeed. In particular, DeepSpeed is able to train the BERT large model in 44 minutes using 1024 NVIDIA V100 GPUs in DGX2 boxes. This is 23 minutes faster than the previously reported time of 67 minutes by NVIDIA, where they use the same number and generation of GPUs. The table here shows how DeepSpeed scales as we increase the number of DGX2 boxes. So for example, on a single DGX2 box, which contains 16 GPUs, DeepSpeed is able to train the BERT model in just over 33 minutes. Moreover, DeepSpeed scales roughly linearly as we increase the number of DGX2 boxes, leading up to the 44 minutes training time on 64 DGX2 boxes. In terms of the techniques that enable DeepSpeed to achieve this results, there are two classes of techniques. The one class targets single GPU performance, and these are the efficiency optimizations. And the second class of techniques are the effectiveness optimizations, which target convergence tuning in a distributed or large batch scaling scenario. For the single GPU optimizations, basically two classes as well. We've developed optimized kernels for transformer computation, and this includes the kernel fusion and invertible operations. And the second class of single GPU optimizations are the model changes, the model optimizations, which include overlapping I/O with computation and exploiting sparsity in the output processing. Collectively, these single GPU optimizations enable us to achieve over 50% of the peak throughput of the V100 GPU. In the effectiveness side, the techniques here include mixed sequence line training, because we're training on a batch size of 64,000, pre-layer normalization, LAMB optimizer, and learning rate schedules. Collectively, these techniques enable us to converge using just 82% of the data samples compared to the baseline. So now I'll start with the single GPU optimization, specifically kernel fusion. The figure here shows the transformer computations in BERT, and specifically the colored boxes show the subcomputations, such as the query, key, and value gems. And each one of these subcomputations requires a kernel call for execution. And since kernel calls themselves come with an overhead, one of the benefits of fusing these kernels together is to reduce the overhead of kernel invocations. Secondly, when we fuse these kernels together, we increase the amount of work that's done within each kernel, and thereby we're able to improve the GPU utilization. Also, by fusing kernels together, we're able to reduce the amount of memory access to global memory, Thereby, we improve the data locality and simultaneously reduce the memory bandwidth requirements to the global memory. In BERT, we identify two classes of kernels that can be fused. The first class are the parallel kernels, such as the query key value gems, which execute independently and therefore can be fused easily. And then the producer-consumer kernels, such as the residual input to dropout and the normalization, which takes in the output. This can also easily be fused together. So as an example, let us examine how we fuse the QKV, or the query key value gems, and the corresponding transform kernels. And in this fusion, we'll be highlighting how they help to improve data locality and reduce memory bandwidth requirements. So the figure here on the left is showing the typical query key value execution in a normal PyTorch. Here, the forward pass, data flow for the forward pass is highlighted with the blue lines, while the data flow for the backward pass is highlighted with the red lines. And on the right-hand side is the fused version that's done by DeepSpeed. Here we see that during the forward pass, the query key value have all been fused into a single kernel, and on the backward pass, the transforms of this gems have also been fused. And what I'd like to draw your attention to is that in terms of the reads and writes that are done by these kernels. So if we consider first during the forward pass, we see that on the query key value all individually read from global memory, so there are 3 reads. But once they are fused together, this can be reduced to a single read. Similarly, on the backward pass, the kernels also make 3 writes to global memory in the default case, but after fusion, this can be reduced to a single write. The second class of GPU optimizations are the invertible operations. So invertible operations are operations for which we can compute the gradients without using the input activation values. And we're able to do this by just algebraic reformulation of the gradient computation. The benefit of invertible operations is that they help to reduce the activation memory footprint, because during the forward pass, we no longer need to save the activation memory for the backward pass. And the transformer, we identify two classes of operations that are invertible in nature: the softmax and the layer normalization. To illustrate, let me talk a little bit about the invertible softmax. Here on the left-hand side, we show the softmax computation graph in normal PyTorch. And the thing to keep in mind here is draw attention to is that the gradient computation here is dependent on the inputs x1 through xn. So therefore, during the forward pass, we need to store this activation so that it can be used during the backward pass. But in DeepSpeed, by exploiting the invertible nature of the softmax computation, you can see here that the gradient computation is no longer dependent on x1 through xn, and thereby we don't need to store these activations. And that way we can save memory by avoiding the memory footprint of storing the activations. The other single GPU optimizations that we have, as we discussed earlier, are done on the model level. And so in particular, there are two classes. The first is the overlapping of I/O and computation. And here the idea basically is that while the GPU is processing the current batch, we can prefetch the next batch into CPU and perform all required pre-processing steps such as the tokenization and others. And by doing this, we're able to avoid doing the data loading from disk, and the tokenization and other pre-processing, we can avoid doing those on the critical path. The other class of optimizations we have are the sparse output processing. So we observed that in the output of BERT, the loss is only computed on only 15% of the output tokens. So all the other tokens are basically discarded. And so by leveraging this observation, we're able to reduce a number of computations that take place on the output tokens, such as projecting from the hidden dimension to the vocabulary size, and then running cross entropy on this output tokens. So overall, we're able to reduce these computations by 85%. And this is illustrated here, where we show that show basically the output tokens on the hidden dimension and the sequence and batch dimensions. By leveraging the fact that we have a mask that tells us which of these tokens are required, we're able to shrink the output by 85%. And using all of this, we're able to improve the single GPU performance. So now let's consider the impact of these optimizations on the single GPU performance. First, let's start with the sequence length 128 phase of the training, or some might call it phase one training. Here, this figure is comparing the performance of DeepSpeed with NVIDIA and Hugging Face kernels. On the x-axis, we have the microbatch size. On the y-axis, we have the throughput, first in samples per second, and secondly in the hardware throughput in teraflops. There are two observations that we can make from here. The first is that DeepSpeed is able to train with larger batch sizes compared to the baseline, in fact, up to 80% larger batch sizes. The second observation is that DeepSpeed is trained with a higher throughput, 26% faster compared to the baselines. Now let's consider the sequence length 512 training performance. Here, our observation is that DeepSpeed is still able to train with 80% larger batch sizes compared to NVIDIA and Hugging Face, and the improvement, the speed up here is 28% in terms of higher throughput compared to the baselines. Now we move on to the effectiveness optimizations. These are the optimizations that target the convergence for large batch scaling. So the first class that we'll look at is the layer normalization. So layer normalization is a technique that is applied when we train with very large batch sizes to improve the training stability. It helps to avoid vanishing and exploding gradients. And so there's a key choice to be made here in terms of where the normalization is placed. There are two options. One is you could place it before the attention layer, the attention module, which is known as pre-LN, or you could place it after the attention, which is known as the post-LN. And here we illustrate both the pre-LN and the post-LN here. And the placement really has an impact, really affects the ability to train at the batch size of 64K. So as the figure here shows, we see that with the post-LN, the model actually diverges as we train, whereas with the pre-LN, we're able to train effectively and avoid divergence. The second class of effectiveness optimization are the LAMB optimizer and the learning rate schedule. And here the thing to point out here that LAMB optimizer enables us to do layer-wise gradient adaptation, which is also very important when you're training with very large batch sizes. And the customization we made to the standard LAMB optimizer is we made it configurable for users to specify the min and max coefficients. The figure here is showing the histogram of the gradient coefficients when training in the sequence 128 and sequence 512 phases of the training. And here we're showing the actual coefficient setting that we use for our training, which is we set the min and max to be between 0.01 and 0.3. The learning rate schedule that we use is a cyclic schedule with decay, and the key thing to just point out here is that we do a re-warm-up as we switch from the first phase to the other, from the sequence 128 phase to the sequence 512 phase. We observe that doing this re-warm-up is very important for training stability, otherwise we're not able to converge as fast. And so in summary, we're able to achieve the fastest training time for BERT model using DeepSpeed. And we're able to do this using two classes of optimizations that are independent and therefore have a multiplicative effect. The first class of optimizations are the efficiency optimizations that target single GPU performance, and which these optimizations enable us to exceed 50% of the V100 peak throughput. The second class of optimizations are the convergence tuning, which enable us to train to converge with roughly 82% of the data samples compared to the baseline. And the great news about these optimizations is that they can widely be applicable to other transformer models beyond BERT. Now we'll switch to the next example model, which is an RNN-based production model known as RScan. So RScan is a production model used in Bing to measure similarities between query and passages. RScan is based on bidirectional RNNs, as shown here in this figure. So here we see that the query and the passage are fed into hybrid embeddings, which include in convolutions. And this embeddings are fed into a bidirectional RNN, which then feeds into a residual classifier to generate the final output. So the objective for RScan was to scale it up to use multiple GPUs effectively in other words, to speed up, to enable faster convergence to the target AUC score. This AUC score had already been achieved on a single GPU baseline. And so the goal was to see how well could DeepSpeed help to speed up the convergence. And the high-level result was that with DeepSpeed, we're able to achieve over 15x speed up on 8 GPUs compared to the 1 GPU baseline. To explain this superlinear speed up, I'll use the table that I presented here. So the speed up table is comparing the baseline 1 GPU, the baseline 8 GPU, which is basically using some off-the-shelf parallelization technique, and then the DeepSpeed 8 GPU. And there are three columns in terms of the speed up results. So the first column talks about the efficiency, which is basically how fast is the system processing data samples. So this is in samples per second. And here the baseline, of course, is 1x. The baseline 8 GPU achieved a decent 5.8x speed up, but with DeepSpeed, we're able to achieve an 8.7x speed up. And I'll go into more details a little bit later in terms of this results. The second column is the effectiveness speed up. And so here, what we're looking at is how many data samples did it take to achieve the target AUC score. And here, the baseline achieves it is basically 1x. The baseline parallelization technique did not achieve the target AUC. So in other words, even though the model was running faster on 8 GPUs, it was not converging to a satisfactory performance, and therefore it was pretty much not very useful. Whereas on DeepSpeed, not only are we able to match, we exceed the effectiveness, the baseline 1 GPU in terms of effectiveness. So we're able to converge using fewer data samples compared to the 1 GPU case. And this efficiency and effectiveness techniques are orthogonal, right? So one is basically talking about how fast are data samples being processed in the system. The other is looking into how many data samples it takes to convert to an acceptable model performance. And so these two can be combined together to get the wall clock speed up, which is we can look at that as how long in time does it take to get to the acceptable performance. And here, for the baseline 1 GPU is 1x here, the baseline 8 GPU is basically 0 because it never achieved the target AUC, but with DeepSpeed we see that it achieves it in over 15x faster compared to the 1 GPU baseline. So let's break down this superlinear speed up of DeepSpeed on our scan, starting with the efficiency improvements. So the efficiency improvements collectively give a 8.7x scaling, and this comes from both compute and communication optimizations. The compute optimizations provided 29% improvement, and this essentially comes from custom kernels that we wrote to improve the execution on a single GPU. The communication optimizations, which provide close to 7x scaling, come from a custom all reduce, which helps to reduce the overhead of doing an all reduce during execution, and then exploiting sparsity in the gradients during the all reduce. So let me dive a little bit deeper into the sparsity optimizations by starting here with showing what we'll consider the dense representation for gradients. So imagine we had a two-dimensional tensor here, and here we see 14 gradients that are about to be reduced. So the first thing we exploit here is the observation that some of these gradients are actually zeros. And this corresponds to weights that are not going to be changed. And this would typically be true for things like embeddings. And so we can exploit the sparsity here by basically eliminating the zeros so that we don't have to be transferred over the wire. And thereby we can shrink the size, the payload of the all reduce, and this is what we've done here, and we convert this into things called index slices. So we need the indices to be able to remember which values are all zeros and which gradients need to be updated. Then the next observation that we made from index slices is that some of these gradient updates are going to the same parameters. And so, in other words, there are duplicates in this in our gradient updates, and that's true because in the same model, the same parameter might be updated multiple times in a batch. And so, what we do next is to deduplicate the gradients. And here we've highlighted in color that we have just three unique model parameters that are being updated by these gradients. We exploit the fact that the gradients are basically added in, so it's a sum, and so we can deduplicate this and reduce that into the unique set of gradient model parameters that will be updated by gradients. And by this exploiting sparsity, we're able to go from a dense representation, which had, in this example, it had 14 gradients, and shrinking down to basically just 3. And so these optimizations collectively provide close to a 9x scaling compared to the single GPU baseline. So now we switch over to the convergence optimizations, which collectively bring us 1.8x improvements in the training time of our scan. The challenge here is that as we train on more GPUs, which means that we train with larger batch sizes, convergence tends to slow down. So in other words, it's been observed that as you scale your batch sizes up, your convergence slows down. And the reason for this is that your model gets updated less frequently compared to the smaller batch size. So for example, if you're training on 8 GPUs, your model will be updated 1/8 as frequently as if you were training on a single GPU. And this comes from the fact that usually when you've tuned your model to converge well on a single GPU on a smaller batch size, the set of hyperparameters that were found to be optimal for the small batch size case are rarely ever optimal for the large batch size case. And so to address this, solutions have been proposed, such as scaling up the learning rate linearly as you scale up the batch size. But fortunately, this does not always work. Sometimes it leads to slow convergence, or it could actually lead to a model divergence. And so we illustrate this challenge here with a figure here where on the x-axis, we're showing the data samples for training, and on the y-axis, we're showing the AUC, which is sort of the the performance metric for the RScan model. And the goal is to see how many samples does it take for RScan to convert to the target AUC. The gray curve shows the 1 GPU baseline, and which we see converges to target AUC in about just under 15 million data samples. The blue curve shows when we scale onto an 8 GPU training, but using the same, and we linearly scale up the learning rates. And here we see that even though the model does converge, it requires more data samples to converge, which is not acceptable. And then when we scale up the learning rate even more to see if that could help to converge even faster, which is a red curve, we see that the model just simply diverges. So to address this challenge of convergence for large batch sizes, in DeepSpeed, we use adaptive hyperparameter tuning. The basic idea here is that important hyperparameters such as learning rate and momentum should not have a fixed value throughout training, as will be done typically, but rather these hyperparameters should be adapted, should be changed dynamically to adapt to the different phases of training, of different phases that the model goes through during training. We've implemented the cyclic schedule that has been proposed in literature. We implemented a variant of that known as one cycle with decay. We've implemented this for the learning rate and for momentum. And this we found to be effective for enabling RScan to converge faster on 8 GPUs compared to the single GPU baseline. We show the results here in this figure. The green curve corresponds to the cyclic schedule on 8 GPU, comparing with the gray curve, which is the baseline on single GPU. We see here that DeepSpeed RScan with cyclic schedule converges in just under 8 million samples, which is almost half of the data samples required by the baseline 1 GPU. To give you an idea of what the cyclic schedule looks like, we show here the learning rate schedule. On the x-axis, we have the data samples, but in this case, we're presenting it in log scale. And on the y-axis, we have the learning rate values that are used at different points during training. The green curve is the cyclic schedule, and as we can see, it starts out from a particular learning rate value and increases over time until it hits a peak, and then it declines in a cyclic fashion. And when it declines to a minimum, it then starts to decay as time goes on. This can be compared to the other curves there, which show sort of the fixed learning rate settings for that is typically used. So the gray curve, for example, corresponds to the single GPU baseline. The blue curve corresponds to the baseline on 8 GPU, where we used a linearly scaled 8 times higher learning rate, while the red curve corresponds to scaling even higher, which led to the model diverging. One thing to observe here is that even though the model diverged when we use a very high learning rate, it's not because the model could not sustain that, but rather it's because the model could not sustain it at every point during the training. So because we see that with the green curve, we train with a learning rate that's even larger than the red curve, which means that as long as we can intelligently adapt the learning rate values, the model is able to train with even larger learning rates, which enables it to converge faster when we use very large batch sizes. To conclude this section, I want to address some natural questions that are probably obvious to you at this point about how, when you're thinking of how to tune a one-cycle schedule for your model. So some of these questions are, how do I set the learning rate boundaries? In other words, what should be the mean and max learning rate that I should use for my model? What is my cycle span? Like how wide should my cycle be? And what's my decay schedule? Basically, how often should I decay and by how much should I decay? And DeepSpeed provides some tools to help the model scientists automate answering these questions. And one of such tools, which I'll focus on today, is the learning rate range test schedule. This is used for detecting the learning rate boundaries for your model. And basically the way it works is that we train the model and we increase the learning rate throughout the training until the model actually diverges. And the learning rate at the point just before the divergence is the maximum learning rate for the schedule. So in other words, this is the maximum learning rate that a model can sustain during training without diverging. And once we have the maximum learning rate, we can figure out the minimum learning rate. Literature's suggested that the minimum learning rate should simply be a fraction of the maximum learning rate. And the literature also suggested that a range between 3 to 10 is a reasonable factor for computing the minimum learning rate, given a maximum learning rate. An appealing part of learning rate range test is the fact that it's very cheap. In other words, you only need a very small portion of your data samples in order to figure this out. And for RScan specifically, we were able to effectively tune a one-cycle schedule using less than 2% of the data samples. Here we illustrate the range test experience for RScan. On the x-axis, we have the data samples in millions, and on the y-axis, we are overlaying the AUC, which is the primary metric, with the learning rate values. And as you can see here, we see that we increase the learning rate throughout the training, and eventually the AUC falls at the point where the model is diverging. And the learning rate just before that point is the maximum learning rate that we use for training RScan. Secondly, we also sort of have an idea, see here that the cycle span is also defined here, because it basically tells us how long should we increase the learning rate in terms of data samples, which defines like how long should the increased portion of the cycle be. And since we use symmetric cycles, that means it's also defined how long the other side when the learning rate is dropping. In summary, DeepSpeed enables the RScan model to converge over 15 times faster on 8 GPUs compared to a single GPU baseline. These improvements come from two classes of optimizations that DeepSpeed provides. The efficiency optimizations deliver an 8.7x speedup, while the effectiveness optimizations deliver a 1.8x speedup. Because these optimizations are orthogonal and complementary, their effect is multiplicative, giving us the superlinear improvements in training. With that, we've come to the conclusion of this section of the tutorial. Thank you very much for your attention. Now, I'll discuss how we achieve.
All right. Now we'll switch to the next portion of the tutorial with a hands-on piece. Just 1 second. Hello. Hello. So Jeff Rasley. I'm here as part of the DeepSpeed team, and we're going to do a deep dive with DeepSpeed today to talk about a handful of different things. So as a rough outline of this segment, we're first going to talk about kind of Docker setup and getting DeepSpeed installed in your system, how to run your training job across either a single node or multiple nodes, how to apply DeepSpeed to your model. So like in this case, we're going to look at the BERT pre-training model. And then sort of the main part is we want to show kind of some performance impact of different features of DeepSpeed. So we'll talk about kind of what the impact is of mixed precision trainings, the use of our DeepSpeed transformer kernel, what kind of speeds you would see there, and then one feature of DeepSpeed which lets you use gradient accumulation. And then finally, the last piece is we'll talk about the Megatron model. This is NVIDIA's implementation of GPT-style models. And we'll apply DeepSpeed and the Zero Optimizer to this model, and we'll see kind of some of the performance impact of that. So yeah, let's get started. So I've put a few links here. One is to our DeepSpeed website. We have deepspeed.ai here. You can go get lots of resources in terms of tutorials and documentation, link to our GitHub page, configuration info. But one thing you might check out first is there's just this getting started guide. So this guide will kind of take you through some of the steps that we're going to talk about today in terms of modifying your model, getting set up, installing, and so forth. But let's the other thing is we have created a GitHub repo just for this KDD tutorial. So it has several scripts that I'll be using today on there, so you can take a look by yourself or give them a try. It does have several kind of submodules to it, so I would recommend checking it out as a recursive, so like git clone recursive in this case. But yes, so let's use this. So what we have so far here. I have access to, I've SSH'd into 2 nodes. So these are Azure machines that are sort of similar to NVIDIA's DGX1 boxes. So each node has 8 NVIDIA V100s with 32 gigs of memory per GPU. As we can see here in the NVIDIA SMI. Now this is the first worker node, and this is the second over here. It also has the same config. These have InfiniBand, so we can kind of see there's one InfiniBand card with a rate of 100 gigabits per second. And this, we've SSH'd in here to the host OS, so we're going to be using Docker today to run one Docker container per node. But we'll start out with this node here. So I've already checked out the DeepSpeed KDD 2020 tutorial repo. as you can see here, we have the link to our DeepSpeed repo, and then we have this folder Docker setup, which we can go into now to get kind of started. So the first thing we want to do is essentially in this script here, what we're going to be doing is we're going to launch a Docker container called DeepSpeed that will be using our DeepSpeed image. This is the latest image. This will contain kind of the latest version, or pre-installed the latest version of DeepSpeed. So we'll pull that image, and then we're going to mount 2 paths from our host OS into the container. Some parts of this are kind of up to you and your setup, but this is kind of how we're going to do it today. The first is we have a local path on this host OS that has some training data already downloaded to it. And then the second is we're mapping the SSH config path. So this has our keys and a few other sort of configs already set up that we'll go over shortly. So we'll mount these 2 paths into our Docker container. We're going to pass the host networking devices into the container, and we're going to pass all the GPUs as well. So this Docker container will see all 8 of the V100s on this node. And we're going to run it in detached mode so we can kind of detach and reattach if needed over time. Let's say if we're running a long experiment, we might want to do something like that, right? Cool. And then the target where we're mounting these is the training data, and our KDD repo will be in /data in the new container. And there's a user called DeepSpeed in our new container, and we'll sort of map these .ssh configs there. Okay. So I've already pulled the latest version of this, so we don't have to pull anything new, just to save some time. But now it looks like good. We've started our Docker container. Everything is good. So now let's take a look at this next script. Just a very basic kind of wrapper script around the attachment to our newly created container called DeepSpeed. So if we attach, cool. Now we're inside our new Docker container. We can see NVIDIA SMI reports all our GPUs. And let's go to data. Perfect. So this is the mapped DeepSpeed KDD repo. It has the same scripts, but let's go ahead and go into Docker setup. Cool. Now let's do the same thing on this other node. I'll do a little bit quicker since we already did this before. Let's see, so. Okay, now we've attached to this one. Let's go to the same path. There is no, in this case, there is no shared file system between these nodes, which in some cases can be kind of annoying, but in our sort of mainstream setup, we set up a shared file system like NFS or these sorts of things. So, but you can kind of do however you want, I guess, to be able to share your file system. Okay, so now the next thing we need to do is we need to have passwordless SSH set up between all of our worker nodes. So I'll step through kind of how we set that up here. So the first, I've already kind of run through this, but I want to explain, I guess, what we did. So this script, all that it's doing is we pass in a list of worker node IP addresses. So for example, on this other node, if we look at the main Ethernet interface here, this is the IP address here. And we would do the same one here on this first worker node and pass those into the script. That'll iterate over those and create SSH config aliases for them. So inside of our Docker container, we're setting up the SSH server port to be 2222 or 22. Yeah, 2222. And then after that, then we're just going to iterate over all of these IP addresses and create a SSH config, which I'll bring up what that looks like here in a second. But I do want to note one thing is if you're running on Azure or any of the kind of major cloud providers, they typically have some kind of CLI. So like Azure has a CLI, it's command line interface that lets you just pull all of the IP addresses of the worker nodes that you have in your subscription or in your sort of setup. So for example, AZ VM like this would be able to sort of pull those out programmatically, so you could pass those to a script like this. We have several Azure tutorials as well on the DeepSpeed website and the DeepSpeed repo. This is a link to kind of how we kind of use that in our existing scripts if you want to learn more details there. But okay, so if we were to run this, what it would give us is now an SSH config like this. And what's nice about this is now we have aliases set up for each of the worker nodes that we have in our job. So worker 0 would be this node, worker 1 would be the other node in this other tab, and we've turned off host key checking, so we don't have, so if the first time we SSH in, we don't have to get a prompt to save the key. And we've set up the port, the SSH port that we're going to be using. Okay, cool. So we've done that already on both. So let's take a look on this one. SSH config looks good. All right, now the next step is to actually launch the SSH server itself on both nodes. So we have this handy script here. So we're setting up what the port is that we want to use for the SSH server. As you may know, is we want to sort of make sure that we're using a different port than the standard port because the host OS has its own SSH server running, and we don't want to conflict with that one. So in this case, we do all twos. We're just modifying the SSH server's config, and then starting the service, and then we'll just check that the service started correctly. Okay, so let's do that. Okay, starting, looks like it's running, excellent. Let's do that on the other one. Oops. Cool, all right, we are running. Before we test if this works or not, let's do one last step. So let's go back to this worker. Okay, so the last and kind of final requirement that we have with DeepSpeed is to create kind of an MPI style host file. So what this does is it sort of maps back to the SSH config on whatever SSH aliases you have set up. So worker 0, worker 1, worker 2, so forth, and how many GPUs each node has. So these are kind of term slots. So we're going to just create this sort of statically for this setup, and then put that in a location called /job/host file. But you could put this kind of anywhere. DeepSpeed just kind of looks to this path by default first. Cool. So let's create that. Now we can see job host file. Perfect. Now let's do it on this side. Make sure it exists. Looks good. All right, now let's give this a try. So if we SSH into worker 1, we should be able to just run a command like hostname. Cool. So what this says is we're SSH'd into that other worker. We got its hostname. We see that its hostname is the same here. So let's do worker 0. Oh, okay. Whoops, so I swapped this is actually worker 0 and this is worker 1, but that's okay. So we see that the host names are different for worker 1 and worker 0. Now we have, so DeepSpeed also installs this tool. It's a kind of a parallel SSH wrapper. So let me show you what this looks like. What this is doing is it uses PDSH to do a parallel SSH across all your workers. And it will kind of look for this host file, the job host file that we defined earlier. So what we can do now is do DSSSH hostname, and there we go. So worker 0 returns this, worker 1 returns this, and we could pass in anything here. So we can do like date, for example. Cool, and it'll sort of prefix the standard out with what worker it's coming from. All right, so I think we're set up. Let's try on this side too, just as a sanity check. Looks good. All right, so now I think we are mostly set in terms of our Docker configuration. Now let's go ahead and try just a simple test with DeepSpeed. Because remember this, since we use the DeepSpeed Docker image, DeepSpeed's already installed. So we have this simple test file in the root of this of our KDD repo. All this is doing is it's going to, it expects some local rank. So this rank is, let's say, the GPU ID that DeepSpeed has sent, or is sort of DeepSpeed has assigned a process for each rank, and it'll pass in an argument for local rank to tell you which local GPU you've been assigned. So this just uses the argument parser to pull out that information, and then we're just going to print that out so we can kind of see how this works. Cool. So to do this, we can use our DeepSpeed launcher. Let me just do help here so you can kind of see what that looks like. Pass in various different things. For example, if you created your host file in a different path, you could specify which path you want to use. We also support kind of more complicated include or exclude flags, and I'll go over those in a second. But the main sort of arguments that you want to pass are just the user script. So in this case, this test.py, and maybe some arguments that you might want to pass to your user script. So DeepSpeed test.py. Cool. So what's happening now is if we scroll up, we can see, okay, it's setting up a sort of a master IP address for the job from worker 0. It's running on these following nodes, lots of sort of verbose logging here in terms of how it's setting things up. It's setting up CUDA visible devices to use all the GPUs, outputting a few other different things. But once we go down here, we can actually see that it launched 16 individual processes, and it'll show what the corresponding local ranks are. So for example, we have this one, which is on worker 0 using GPU 1. And then we have worker 1 also using its GPU 1. Cool. So one other thing I want to show is this include or exclude argument is kind of nice if you want to run, let's say we want to run a job only on one worker, but we have a host file that includes numerous workers. We can do worker 1, and we can even say, let's just run on GPUs 3, 5, and 6. So now if we run this, we see that we're only running on worker 1, and the local ranks here are 0, 1, 2, but our CUDA visible devices are sort of mapping our GPUs 3, 5, and 6 that we called in here to those ranks. So we can specifically kind of assign GPUs here if we want. Exclude also works in a similar way. And you can specify more than one worker. So we could do like worker 2 here, for example. Cool. So let's see. The next thing I want to show is how to install DeepSpeed. If, let's say, you want to make some modifications, or if DeepSpeed has changed since you last updated your Docker image. Okay, so we have the DeepSpeed repo here that points to this repo with all of our latest code. As you can see, we've made some changes about 3 hours ago even from when I recorded this. But let's see, so we have a handy install script here. Let me do help so we can kind of show how this works. So what this install script does is a few different things. One thing that we've found, especially when developing DeepSpeed, is that we commonly have multiple sort of nodes in a job. So in this case, we have 2 nodes in this job. And we want to install reinstall DeepSpeed if we're sort of doing some development or adding some new feature, and we want to install it across the entire cluster, I guess, of our job. So like across two nodes, for example. And a pip install would typically just install this in the local node. So we'd have to do maybe a bunch of pip installs in parallel, or do build a wheel and then SCP the wheel around, or these sorts of things. So essentially this install script kind of just helps with that. So by default, it's going to, if it finds this job host file, it's going to install DeepSpeed and all of its requirements across your entire job or across all the worker nodes in this file. If you don't want to do that, there's an override. So you can just do a local install, for example. In addition, so inside this Docker container, at least we're sort of installing into the OS path. So maybe we'd need sudo to actually do the installation. Does clean builds, but you can turn those off. Various kind of things here. And one dependency DeepSpeed has is on Apex, so you could kind of just install DeepSpeed and not reinstall Apex if you want, or you could. So in this case, let's just do DeepSpeed only, and we will do a pip sudo. And go. This will take a couple minutes, but not too bad. So I'm going to pause the recording for now, and then we'll come back after this is installed and do a few more fun things. Right, so we're back. Got my coffee, we're ready to go. So where we left off was we were starting the DeepSpeed install. It takes a couple minutes, so that's why I ran to get some coffee. But now we are fully compiled and it looks like we're installed. What's great is that, as I was saying earlier, is we were installing this across both of our nodes. So what we can see is worker 0 successfully installed DeepSpeed 0.2. And we can find that same message for worker 1. In addition, at the end of the install here, we can kind of see some checks have kind of successfully occurred. So one is we check to see if we can import DeepSpeed. We're checking the Torch version that was installed, what git commit hash was used for this DeepSpeed install. The branch in this case was just head. Our Apex dependency looks good. We have some DeepSpeed CUDA kernels that looks like we can access, so that's great. And yeah, we're overall successful, so this is good. So the next thing, if we go back to our outline here, so we've just talked about Docker setup and install. We've run just a basic test script that just launches, kind of just does a print hello world kind of thing across a single node and multiple nodes. And now we want to talk about applying DeepSpeed to a real model so that we can actually check out some of this fun performance stuff. Okay, so let's take a look at the BERT model. So in this directory here, we see we have access to the DeepSpeed repo, and inside the DeepSpeed repo, we have a submodule that connects to our DeepSpeed examples repo. So if we go inside there, we have several different types of models. Squad, fine-tuning task, Megatron from NVIDIA, Bing BERT, which is this BERT pre-training we're going to talk about today, and then like a simple like C for example as well. Okay, so let's go into the Bing BERT folder, and we can see several things. So we see some JSON files, some bash scripts, DeepSpeed train, this kind of stuff. So let's actually dig into the code and take a look at what's going on. So I have a VS Code session set up now, and it's on a local copy of the DeepSpeed repo with the DeepSpeed examples. And we can see here a similar kind of setup. If we go into DeepSpeed examples, I'm going to go into Bing BERT, and we see the same kind of setup here. So let's look first at DeepSpeed train. So from the top, a bigger file. So let's just minimize all of these methods here just to, so we can sort of more easily navigate and see what's going on. Cool. Okay, so when we launch DeepSpeed Train for BERT, we're going to hit this main function here, and it's going to do a couple things. So the first thing, we're going to construct some arguments. So let's look at those. So that does a few different things. We're not going to go into all the details, but just the DeepSpeed kind of specific parts. So get arguments is here, and get argument parser is here. So get argument parser actually comes from this utils class. Let's go to utils, go to the top. So get argument parser is just creating a Python argument parser and then adding several sort of user configuration flags. So these are things like setting the max sequence length for training, output directories, lots of kind of specific things to this model. But what we need to do with DeepSpeed is we want to include DeepSpeed's configuration arguments. So DeepSpeed has a few additional arguments that are added to Python's argparse. So we can call into the DeepSpeed library that we've imported and just add them here. So it modifies the parser, and then we just parse our arguments like we would normally, and we can proceed. Also, I wanted to point out is the getting started guide for DeepSpeed is here. So it's DeepSpeed AI, and then there's a getting started. And what we can see here is there's a couple kind of steps in general. So there's DeepSpeed initialize, which we'll get to in a second, the actual training, and then the argparse is somewhere in here as well. So that we just had here. So there's the argparse addition. Now let's backtrack a little bit. So we did that. The rest of this are kind of specific to this BERT model or just model training in general. Let's see, cool. So let's minimize this, go back to the main. So we've now have some parsed arguments from Python, and we want to prepare the model and optimizer. So what does that do? This goes into a few things. So we're in this case, we're initializing PyTorch's distributed backend. You don't necessarily need to do this. If you want DeepSpeed initialize, we'll actually do that for you. But the first step here is actually instantiating the model. So this is loading the model, the BERT pre-training model itself. And then once the model's instantiated, then we will call DeepSpeed initialize. So this is kind of one of the first main API calls into DeepSpeed. And what this does is it's going to wrap the model itself in kind of to support data parallelism and all the sort of fun features that we're going to sort of showcase today. But before we kind of dig into that, let's look and see what BERT multitask actually is doing. So we're passing the args. BERT multitask is actually coming from here. So go into models, down, so BERT multitask. So this is specific to this model. It has kind of a wrapper class around the NN module, which is the actual torch NN module. But let's find the torch NN module here. So if we scroll down when it's initialized, here we go, BERT for pre-training pre-LN. So this is actually the sort of BERT pre-training NN module itself. So we're saving it into this self.network field. Let's see, so that's essentially it for the model itself. This BERT for pre-training pre-LN actually comes from here. I search for this, so there it is. So you can see, if you're curious kind of into the specifics of this BERT model, I urge you to check out this file, but there's a lot of fun stuff in here. So now let's go back. So we have instantiated our model. This is how the model is instantiated. We go back, here's the model, and now prepare optimizer parameters. What's this doing? This is essentially setting up weight decay for all the parameters in the model. So you can do kind of iterate over the parameters and set those flags up. Now DeepSpeed initialize is getting past the arguments that the Python arguments that we modified earlier. It's being passed to the NN module. So this is the model.network in this case, but maybe just it's in most cases, this will just be the model. And then it's getting past these modified optimizer parameters. So this is how we're going to let DeepSpeed instantiate our optimizer. And I'll show you in 1 second how that's done. That's done through our DeepSpeed config JSON. But yeah, let's go over that now. So the rest of this actually is what's happening here is we're pulling out, so DeepSpeed kind of keeps track of various parameters such as the batch size and gradient accumulation steps and these sorts of things. So those are all going to be done here. You don't necessarily need to do this, this kind of specific to this BERT model. Okay, so let's bring this up. So this is the DeepSpeed JSON config. So this is going to be passed in when we actually run DeepSpeed so that you can turn sort of on different features or turn off different features of DeepSpeed. So for example, let's step through this here. So all of this is documented in this configuration page, so DeepSpeed configuration JSON. This lists out all of the keys and default values of this JSON, so you can kind of get an understanding for what they're all going to do. But I'll go over each of them for this model first. Okay, so train batch size. So this is the total training batch size across all GPUs that you're training with. So in this case, it's essentially 64K. And that's, you could think about that as how many samples are we going to train over between each optimizer step. And then the train microbatch size per GPU is the instantaneous amount of samples that each GPU will hold at any given time. So in this case, 32 gig V100s, we can fit, we know with this setup, we can fit 64 samples per GPU each time. This steps per print is just kind of for logging. So like every 1,000 steps, we'll print out some logging information. So this is just the default value for this in case some advanced features. But then the interesting part now is the optimizer. So in this case, and specifically in the case of our record of training BERT large and really fast, we used, and many people as well use, this LAM optimizer. So you can actually use LAM by just specifying it here. You don't have to instantiate it in your code in any place. You can also switch to, let's say, Atom if you want, just by changing this word LAM to Atom, essentially, and changing whatever parameters you want to pass to it. But this sub-dictionary here called params are the parameters of the optimizer. So what will happen is DeepSpeed will instantiate this LAM optimizer, and then it will instantiate it with these initial configurations. So like the initial learning rate, weight decay values, these are some LAM specific parameters as well. And yes, so then outside the optimizer, we have gradient clipping. So if you want to do any kind of gradient clipping in your setup, you can specify that value here. DeepSpeed also provides some profiling. So in this case, wall clock breakdown, which will give you kind of a wall clock timing information about how long your forward pass, backward pass, all reduced times, these sorts of things, how long those are taking, so you can kind of understand the performance breakdown of your training. Currently, we'll just leave that off for now. And then finally, the last feature we'll talk about in this setup is mixed precision. So if you want to train with half precision, so FP16, which is definitely recommended, especially on V100s. So this NVIDIA V100 GPUs have what are called tensor cores, which allow you to sort of accelerate your training a bit further, or significantly further, I should say, if your model is kind of set up to use half precision. But there's lots of sort of additional complexity that's added if you try and train with half precision. So DeepSpeed kind of helps you reduce that complexity by just kind of letting you turn on and off this mode, and it'll handle just about everything else for you. Let's see. So that's pretty much it for the DeepSpeed config JSON. Now let's go back to the DeepSpeed train code. So this is the actual client sort of code for BERT pre-training. So now we understand the DeepSpeed initialize call here. We did the DeepSpeed configuration JSON. And now the final piece that we have to change in our model is sort of how we are doing the actual training loop itself. So let's minimize this. Now what's happening now? Let's see. So if we're loading a checkpoint, cool. But now this run, let's go to this run function here. So what's happening here is it's loading different shards of data and then feeding those shards to this train loop. So let's go to train. We're getting some training data sets. In this case, this is going to be getting the book corpus and Wikipedia data sets and kind of interleaving those during training. And go. So now we're going to pick out different batches. So this will be each training step. So then we'll pick out a batch, and then we're going to feed that batch to our model. So in this case, get some loss back for some model. This is our wrapped DeepSpeed model. So this, if you recall, this model object was returned by DeepSpeed initialize and now eventually used in our training loop. So we pass our input batch into the model, get some loss, and then we now do a backward pass. So this is a little bit different than other sort of setups. So that's why I want to kind of point this out, is sometimes in Torch you might do a loss dot, like a loss dot backward. But in this case, the DeepSpeed wrapped model here is kind of handling the backward pass for you by just passing. There's a backward method. We pass the loss in, and it'll do all that. Then DeepSpeed also handles the gradient accumulation sort of feature, which we'll talk a little bit more about later. But eventually we call model.network.step. So what this is this is kind of replacement for your optimizer.step. DeepSpeed will, you can kind of think of the DeepSpeed wrapped model as like a model engine. So that engine then kind of has access to your optimizer and the model and some additional state that it keeps track of. So we do this model network.step to actually do our optimizer step that will update our model weights and so forth. And then that's essentially it on the model side. Everything else is kind of existing code for this BERT model. There we go. So now let's go into, so we talked about the DeepSpeed JSON file, but then how do we actually run this now? Now that we've sort of gone over the main sort of changes that we made to the model, if we go into this shell script here, this is the helper script that we've created to do, that will pick up our DeepSpeed train.py that we just went over, and then also a few JSON config files. So what's happening here is we have some job name, so we can kind of output some checkpoints and so forth to this output directory. And DeepSpeed launcher, so we went over this earlier. So this is the DeepSpeed launcher. So this will launch across all of our GPUs in our job or in our hostname file. And the vast majority of these flags that are being passed are specific to BERT. So for example, there's this BERT large lamb JSON, which is here, that has lots of different configuration flags for BERT itself. So these are BERT model config, then also where the data lives. So where's our training data actually located? And then also some specifics relating to if we're training with a sequence length of 128 or 512, and what our learning rate schedule should be for that, and so forth. Where's our validation set, that kind of stuff. So that's being passed in. So let's go back to our shell script. We're training in this case with sequence length 128. We're enabling DeepSpeed. So this is just in the client code if there's some branches on if we're in DeepSpeed mode or not. We're going to use our DeepSpeed transformer kernel, which I'll show you momentarily kind of how that's set up in this code. And then finally, here is the pointer to our DeepSpeed config JSON. So this is the JSON file that we were just kind of going over, and this is just the path of where DeepSpeed can find this to pull this in, excuse me, and actually turn on or off different features of DeepSpeed. Cool. So the final thing we'll talk about is DeepSpeed transformer kernel before we actually start running this. So let's look at this flag here. So if we go into utils, transformer kernel. Hey, sorry guys, I'm not sure what's going on there. All right, so now that we've made all the code changes to get BERT running with DeepSpeed and gone all over all that, let's now actually run it. So now let's see. So we're going to talk about, in terms of our outline, now we've covered these top 3 pieces now. And now we're just going to go over kind of some performance impact of different features with DeepSpeed and use this BERT model that we just went over to actually run this. So specifically, first we want to talk about single GPU performance, a few different features that DeepSpeed has, and we'll show kind of the impact of those. And then we'll move on to multi-GPU, multi-node kind of situation and kind of show the impact of different interconnect speeds and all that stuff. So first here, we're on our worker node. So let's go into our DeepSpeed examples, and then inside there we have our Bing BERT example. So let's see. So the first thing we want to look at is our DeepSpeed config. And let's run this with FP32, so this is full precision, so we're going to turn off this feature that runs in FP16. We are going to, I know, I guess from prior experience with this, but sometimes it's a little trial and error, so you need to figure out what your sort of best micro batch size is per GPU. So in this case, we're going to run with 1 GPU, and we're going to run with a micro batch size of 32. And that means with 1 GPU, that would be a total batch size, train batch size of 32 as well. Okay, and we have this handy run script created just for kind of this tutorial today, but this will run DeepSpeed. We're going to include just 1 worker node and then 1 GPU on that worker node. And we're going to execute this DeepSpeed train script, which is what we just went over. We have this this BERT large lamb JSON, which I'll bring that back up just as a refresher as well. But the key kind of piece here is the DS config here is turning on and off all these features. So this is what we just looked at. That's we're going to use like full precision training, batch size of 32, all that stuff. So when we run this, it's going to just run on a single GPU with this config. And let's turn off our transformer kernels. So we'll just be running this with basic PyTorch kernels here. And let's see, this looks good. And let me bring this up. So this is the, whoops. This is the sort of BERT config pointing to kind of our training data and learning rate schedule stuff for sequence 128 training at least. Validation data and everything. Cool, so let's go ahead and run this. So again, this is just running on 1 machine. If we scroll up, we can see right here at the top that the world size is 1. We've loaded some training data here, this path, number of samples, how long it took. Kind of gives us a summary of what our DeepSpeed JSON config looks like. So you can kind of see that for your logging purposes later, and also all sorts of other different parameters, what they're set to. And this should start. What we're going to do too is go to this other node, go to worker 1, see what's going on. Cool, so we see that 1 GPU is being used on a memory. There we go, looks like we've started. And in this case, what we see after about 50 steps, this is pretty slow, so this is full precision. This is running at about 43-ish samples per second. Let's let it hit 100 steps and then we'll kind of close this out. But we can use this as kind of a baseline for what we see so far. So let's make a note of this. So this is FP32, 1 GPU, batch size 32, gets us about 43 samples per second. Make this a little bigger for the video. Cool, so we can keep track of this. Okay, let's close this out. The one thing I like to do just to be on the safe side is run this parallel SSH script and just kill all Python processes to kind of make sure that everything's essentially been closed down. And then we can check the running processes as well. Looks like we're good. Okay, so next thing we want to do is let's turn on FP16. So that's simply just change this one line in our JSON config now. And from prior experience, I also know that we can, in this case, we can bump up our batch size. So this means that our input batch size and our model weights and everything are changing from full precision to half precision. So we can actually fit more now in memory. So this, along with a few other things, actually gives us a nice speed improvement. But let's check that out. So everything else can be the same. Let's just run this here. Right, some logging, somewhat verbose. So we see FP16 enabled is true here, so that's great. Doing this data loading just like we did before. Now we're just about to start training. Cool, wow, okay, great. So now if we recall previously what we were at is, so this is one GPU, batch size of 64, now yields us about 179 samples a second. And if we look at NVIDIA SMI again, yeah, we see we might have a little bit more room to increase the batch size a little bit if we wanted to kind of push the boundaries here, but it's pretty high, right? All right, so now let's do one more thing. So this has been running 150 steps. We can see that it's running reasonably fast. We're getting sort of printouts more often of the throughput and such. So let's kill this. Make sure everything's killed, looks good. We can even verify, sometimes nice, just to make sure that everything has kind of been cleaned up okay. There's nothing allocated on our GPUs, that's great. So now let's go ahead and turn on our DeepSpeed transformer kernels. So in this case, we're turning on this flag to replace our BERT layers with DeepSpeed's version of the transformer kernel. And we're also going to use this stochastic mode, gives us a slight speed improvement as well. But I urge you to check out, so we have these, as a reminder here, we have these 2 pages on our DeepSpeed website that kind of go and do a big deep dive. And also Tunji previously talked about this, I believe, in this workshop or this tutorial as well. So some of the features of this. But cool, so all we need to do, at least for this code, is just to add these 2 flags. Everything else essentially stays the same. Now let's run this. So while we wait, let's update our log. So this is FP16 plus kernels, 1 GPU, same batch size. What are we going to get? Cool. Looks good. Let's let it do one more. One thing I want to note here as well is the performance that we see on this machine. This is essentially a DGX1 box. If we compare that to our numbers here that we did for this sort of ultra-fast BERT end-to-end run, they're a little bit different. And the reason for that, and I verified this several times, the reason for this is the machines that we're using here are actually DGX2 boxes. So DGX2s have a handful of different kind of improvements over DGX1s, but in general, we see about a 5-ish% boost in throughput per GPU, or for a single GPU, comparing a DGX1 versus a DGX2. But cool, so yeah, we're about 215. So let's kill this and this. So that's pretty great in terms of single GPU. Now, one other thing is, if you notice here, so let's do this other feature, which is wall clock breakdown. So what wall clock breakdown is going to do is it's going to give us a breakdown of time for each of the components of training. So this is going to give us information on forward pass, backward pass, and optimizer step, and also our gradient reduction step if we're training across multiple GPUs. So let's redo this same run. Let's make sure everything's good. Okay. do the same run, but now just turning on this wall clock breakdown. Excellent. Let me just kill this so we... Okay. So let me scroll up. There's a lot here, but let's just take one sample here of this. So this is showing in milliseconds, forward time, backward time, and our step time. So what we see is every step, or every training step, is doing some optimizer update. So that means that our DS config here is showing a microbatch size of 64, and then every 64 samples we do an optimizer step. So what we could do is, to improve some of this performance, is turn on gradient accumulation steps, and let's do this to 10, let's say. So now I've put an underscore here just to turn off this. Essentially, I just comment this out. So now our effective batch size for this one GPU training is going to be 640, so 64 times 10. So what this will do is it'll essentially, we can kind of amortize the optimizer time over multiple steps. What we'll show in a little bit is this also helps us in our gradient, reducing our gradient reduction time. So on like low bandwidth clusters and stuff as well. But let's try this again now with gradient accumulation set. So now this is FP16 plus kernels plus, and then one GPU, batch size 64, but our gradient accumulation steps are 10. Now, oh, we left wall clock breakdown on. Okay, so it's going a little bit fast through there, but let's find a samples per second. This is kind of hard to see. Let's just turn this on. Sorry about that. Back off. Okay, let's rerun this. What we're expecting here is that just this samples per second is going to boost up a little bit since we're not taking a hit on the optimizer time every training step. The trade-off is that now we're increasing the total batch size a bit, which might have some convergence issues, or yeah. So cool. Right off the bat, we're 236. So that increases our performance slightly, which is nice. Excellent. Okay, so now let me close this and let's move on to multi-node, multi-GPU. So we have this other worker over here just sitting idle, right? And 7 other GPUs on this box. So let's see what happens as we increase that. So let's bring up our DS config again. And we can then, let's turn this off. And so what we actually want to train with in the batch size that we used for the speed run is 64K. So what that means is 65,536. So now each of our 16 GPUs will be running but microbatch size of 64, and then for a total batch size with gradient accumulation of 64K. What's nice is DeepSpeed will actually calculate the appropriate number of gradient accumulation steps needed to satisfy these two constraints. So you don't have to worry about that. And let's see. So now, if we go back to our DS run, one important change here is now we want to run on the entire job, which remember is everything in our job host file. So here, so worker 0, worker 1, both 8, and we will run this with our transformer kernels. It's good. This will also be with some gradient accumulation steps, which is nice. And let's give this a try. So if we see here, world size and 16. Oops, I don't think there was an issue here. Let's. Fun part about a live recording here. Okay. So the issue is on our other node. If you notice, we do not have the same JSON. So this is kind of the issue with the fact that this doesn't have a shared file system. So we have to make sure when we make changes on this node, we propagate those files to the other node as well, either through a shared file system or just SCP them over. So let's go ahead and do that. Specifically, the only thing we've changed here is the dsconfig JSON. So let's do that to worker 0. And the path is here. And we can verify that's over there. Looks good. Now, let's try again. Cool. Lots of logs printing out here. Okay, we're loading our training data set. And notice also we have worker 1 here, worker 0, so we're getting all the logs from all 16 ranks here. And let's go ahead. Well, it looks like we've started to train. So let's look at NVIDIA SMI on this other node. Excellent. So we have a little bit of headroom just like before, but looking good. All the GPUs seem to be working away there. Excellent. So now we're seeing about 3,700 samples per second. Let's go here. So what do we see now per GPU is, so this update our notes here, we have, this is 16 GPUs, batch size, micro batch size 64. And what we see with that is about, let's say 3680 samples per second, which translates to about 230 per GPU, which is pretty good. It's popping back up here about 37, but yeah. So what's nice here is we're seeing pretty great scalability, I guess, in terms of as we scale from 1 GPU to 16 GPUs. The InfiniBand's helping us here. NVLink between GPUs on the single blocks is helping us. Lots of good stuff here. So let me cancel this. I want to show you one more thing relating to this model. And I have another job set of nodes allocated. So this is on a completely different cluster. And what's going on here, I have the same code, but this is a kind of slower cluster. So like it's a different SKU or instance type on Azure, where we have 4 Tesla V100 cards, but only with 16 gigabytes of memory per card. And we have 4 GPUs per node. So in this case, if we look at our job host file, we have 4 worker nodes, each with 4 GPUs. So still have 16 GPUs in total, but we are kind of spreading that across multiple nodes. The other thing is, if we look at IBstat, there's no InfiniBand. We also can look at, I have an iPerf session server running on one of the other nodes. So this is going to do just a basic TCP test to transfer some data between worker 0 and worker 1. So we can kind of get a basic idea of the throughput available, at least via TCP. It's pretty low. So it's, in this case, it's, if we're being generous, maybe 4 gigabits per second, right? But let's see what we can do here. So I'm going to, so we have a different JSON file here. But first, let's try, so in this case, since we only have 16 gigs of memory, we're going to run with a batch size, micro batch size of 32, so that we can actually fit this. And then let's first try gradient accumulation steps of 1. So in this case, our train batch size will actually be calculated as follows. So we're going to, will be 32 times 1 in this case, times 16. So our total train batch size that DeepSpeed will calculate for this and use is 512. This is commented out, so we're not actually using this yet. We're still using LAM optimizer. We're using FP16. We're still going to use our kernels, everything like that. So we'll show this is the run script, kind of looks similar to the other one on the other cluster. We're going to use our transformer kernel, stochastic mode. Yeah, essentially all the same, but just this different cluster with different interconnects and smaller GPU memory. So let's just make sure there's nothing else running. Looks good. Let's launch the training and see what happens. Scroll up, missed it. I was going to show you the world size, but didn't pop up. Let me see. I think I can get it from up here though. So this, so world size here is 16, micro batch 32, train batch size here calculated is at 512. Let's go to the bottom. So I started this with this wall clock breakdown, which is actually great. Open this up a little bit more. So this isn't showing our samples per second yet, but what we see, if we look kind of closely at our all reduced time, so this is backward all reduced microstep. So what this is showing is in milliseconds, so we're taking almost 3 seconds, 3 full seconds to just do the gradient reduction. So if you recall, what's happening is each rank was going to compute its own backward pass of the samples that it's seen. It'll generate its gradients, and then it will all reduce those gradients across all ranks. So there's a communication kind of synchronization point, and then proceed to the next step. Here we go, samples per second, 167. So let's see. So this is 16 GPUs, V100, 16 gig, slow interconnects. So 16 GPUs, batch size 32, gradient accumulation steps 1 gets us at 167 samples a second. This was 16 GPUs too, so like, right, so like this is going to be 167 divided by 16, like 10 samples per second per GPU, right? This is Pretty bad, pretty bad. Okay, so now if we close out of this, if we can get away with running a larger effective batch size, total effective batch size, which we can, this should save us a lot, right? So if let's comment out gradient accumulation steps, we're going to do our train batch size per GPU is 32. Total train batch size this. Just let's show you here 1 second. So if we do some quick math, that's total train batch size divided by micro batch size 32 divided by 16 GPUs. So now 128. So what this means is we're going to do, each GPU is going to do 128 forward and backward passes by itself without coordinating between any other GPUs. And then after it's done 128 of them, it'll do the gradient reduction, which will sort of be that synchronization point, which takes 3 seconds, right? Which 3 seconds is an eternity, right? Like in these sorts of things. So let's see what happens. This should be good. Let's verify. So, yep, that looks good. Now let's make sure that's all good. We can even do this across the whole cluster or the job. If we don't see any other processes running, that's great. And let's just load our launch script. So remember this, we're not passing any include or exclude. So this means that we're going to run over all 16 GPUs. And let's check it out. So now this is same setup, but 128 gradient accumulation steps. And what's that going to give us? So what we'll see, oh, it's going kind of fast. That's good, but it's a little hard to read. So let me kill this. Okay, if we scroll up and see what happened, 3,500 samples per second. What is that? That's pretty wild. Let's rerun that really quick. But I want you to be able to see what's happening. So let me turn off wall clock breakdown. Make sure everything's killed. Okay. I think that's at 3,500, right? That's pretty big difference. But let's double check. So we're in the model initialization. Yeah, look at that. That's great. We could almost fully train this thing now, right? Okay, so 35, 30 samples per second. What's the per GPU? 220. Excellent. That was in the realm of what we were seeing on the per GPU of the 32. That's great. Okay, so it looks like we've dropped a little bit. Ah, yes, okay, so this is an important point. So remember our gradient accumulation steps are 128. So that means right around 120, 130, there's a drop, right? Because we just spent 3 seconds to do that all reduced, right? So if this is samples per second that DeepSpeed outputs here is averaged over time. So if we let this run for a while, we'll kind of converge on the true average, right? But let's, even if we go with the low end, so this is like the 2947. Let's be conservative here. 2947. What is that? 2947 divided by 16, 184. Still excellent. And what is that, 184 divided by 10? Easy math, I guess, but 18x improvement by just increasing our gradient accumulation steps. Not bad. Cool. All right, so I think that's about it for the BERT related stuff that we wanted to go over today. So yeah, we'll take a pause for now, and I'll come back with a few other things relating to Megatron and Zero. All right, so now that we've made all the code changes to get BERT running with DeepSpeed, okay, so now I want to show you all one last video. I want to make sure that everyone can access this last piece. So now, let's see, we're going to talk about, unfortunately, the last got here is our deep dive here, relating to Megatron using DeepSpeed and Zero video. Where we're going to talk about Megatron, Zero, and kind of go into a deep dive of all of that. But instead of that video, we're going to show one last segment, which is part 6, which is going to go over a frequently asked question kind of round with some of the DeepSpeed team. So. And before I start this, yeah, thanks for everybody who's sticking around to the end here. And if you have questions, feel free and add those to the chat, and we'll try and answer those before the end here. So thank you. Hello. So this is kind of the last segment in our tutorial today. But what we wanted to do was kind of go over several questions, kind of frequently asked questions that we commonly get from DeepSpeed users, especially new users. So with that, I will, so we have 3 people on the team here that are on the call right now, but I'm going to act essentially as the user asking these questions. So the first question we have is for Samyam. So when does Zero show sort of the best memory improvements?
Yeah, so most of the memory improvement from Zero is coming from reducing the amount of memory required to store the model states. So these are your parameters, gradients, and optimizer states. So Zero shows improvement if these model states are what is causing the model memory bottleneck during the training. So this is generally true for larger models. So in general, you can think of it as if you're doing mixed precision training and you're using an optimizer like Atom, if you have 1 billion parameters, then your total memory footprint is going to be 16 billion. So you just take the number of parameters in billion and multiply that by 16. That gives you the amount of memory footprint. So if your model states itself is consuming 16 gigabytes of memory, that's quite a lot. So when you use the Zero optimizer, it can reduce that by a factor of 8. So that 16 goes down to 2. So basically, in these cases where you are trying to train a large model with lots of parameters and your memory footprint is large due to these model states, that's when Zero really shows improvement.
Excellent, thank you. So one more Zero question is, does Zero have like a huge performance penalty, or like aren't you doing sort of additional communication or something like that?
Yeah, so that seems to be the common misconception, that we are doing a lot more communication than default data parallelism. We are doing a different type of communication than data parallelism, but we are not doing more communication. So in fact, the 8x memory improvement that I talked about earlier, that is absolutely free. There is absolutely no increase in communication when you use 0 to get the reduction in memory. We do have an additional optimization in 0 that is not currently in DeepSpeed that allows us to decrease the memory even further and has some communication overhead that can impact performance. But currently, the 0 in DeepSpeed that gives us up to 8x memory reduction has no communication overhead, and so it doesn't impact performance. And if anything, since you're reducing the amount of memory required to train the model, you're actually able to increase the batch size. So you'll end up actually seeing a performance boost than a performance degradation. Yeah.
That's excellent. That's excellent. Cool. So one sort of switching gears a little bit, a question relating to BERT, and this is for Tunji, is a lot of people have noticed that like our BERT record, for example, of pre-training and all of our BERT kind of code in the DeepSpeed examples repo sort of assumes that you have access to this like BNORIC data or like this sort of specific data set that you used for training. Since we didn't, like the DeepSpeed folks haven't publicly released that data, like how can I actually train this model using your code?
That's a great question, and the good news is you don't need the BNORIC format anymore. Recently, we just made some changes that allows you to use NVIDIA's dataset. So NVIDIA has a publicly available dataset for pre-training BERT, which includes the Wikipedia and the book corpus data. And we just added support for it. If you look into the README section of our Bing BERT example in the DeepSpeed examples repo, you would see instructions for using that, and it works right out of the box. You don't need to make much changes. We provide you the scripts and the configuration files, so you can simply just launch them and run them. And as long as you have the data set set up, and NVIDIA has very nice instructions on how to prepare the data set, and so once you have that all set up, then you're good to go. And you can train with our DeepSpeed model. You can use our custom transformer kernels. You can use all of the niceties of DeepSpeed while training with the NVIDIA dataset.
Excellent. That's great. One other question is, when I'm training with DeepSpeed, sometimes I notice at the very beginning of my training that I get these strange overflow warnings that are sort of in all caps lock or all caps saying overflow, overflow. Should I be concerned about those, or what's that all about?
Yeah, you really shouldn't be concerned about those. Overflow basically comes from the fact that you're doing the mixed precision training. In other words, you're using FP16 to train in scenarios where sometimes you might require a full 32-bit floating point value. And so what the solution that is typically used is to do a loss scaling of your FP16 values. And so sometimes, and because it's really hard to know what the right loss scale value is, so you started with a value that may not fit, and when it doesn't fit, then the training infrastructure detects that and throws out an overflow and sort of basically skips that example, and it lowers the loss scaling. So basically it's adapting and adjusting the loss scaling so that eventually you wouldn't see the overflows anymore. So seeing overflows at the beginning of your training is nothing to worry about, and if you're really worried about it, you can start with a lower loss scale value. And in DeepSpeed, we do provide you the ability to configure a starting loss scale value, which is much lower, and would basically get rid of the overflows. So it's not something to be concerned about. It's just a part of the regular mixed precision training.
Excellent. Cool. So one last question, and I'll field this myself, I guess, is so I've heard of this feature from NVIDIA Apex called AMP. So they call it automatic mixed precision. So DeepSpeed supports FP16 and mixed precision, and Apex does. Like, how do these sort of relate? So the answer to that, to answer my own question, is essentially the way that DeepSpeed works initially when we first released it is by doing something kind of similar to AMP in terms of what Tunji was just talking about with loss scaling, but it was kind of targeted originally at just sort of one kind of mixed precision mode where just about everything is in FP16 or half precision. So Apex, or the NVIDIA folks, released this package called AMP, which kind of lets you switch between modes. So there's like a sort of partial FP16 and FP32 sort of mixed combination that works well with certain models. And what we recently have released is the ability for DeepSpeed to kind of switch the back end of DeepSpeed to support these different AMP modes. So urge you to check out our website and the DeepSpeed configuration JSON config, and it'll show you kind of how to use that and turn that on if you're interested in that feature. Cool. So with that, I think we'll conclude. Thanks, you guys. Thanks for everybody listening, and bye.
Bye.
Thank you. Bye-bye.
Use DeepSpeed.
Happy deep speeding.
Yay.
All right, cool. Did Jeff drop out?
It's still recording.
Yeah.
I don't know how it's going.
All right. Yeah, thanks, everybody. Thanks for coming and attending our tutorial, and urge you to check out deepspeed.ai for more information about everything we've talked about today. Check out our GitHub, and if you can, give us a star if you like us on GitHub. So excellent. Thanks so much.